All right, so now we're going to work on page 2 from the extra practice. So we spent some time working with synthetic division and all that stuff, so let's continue on with this. So the first thing says to list all possible rational zeros of the function, so this is just the rational zeros test. This is pretty easy. All you need to do is just find the constant value and the lead coefficient. So you put the constant on top, lead coefficient in the bottom, then list off all the factors. So all the factors of 15 are 1, 3, 5, and 15. The factors of 6 are 1, 2, 3, and 6. And then you just make combinations of the fractions involved. So I always just go based off of the denominator. So if I have the denominator of 1, 1 over 1 is 1, so I do plus or minus 1. 3 over 1 is 3, so that's plus or minus 3. 5 over 1 is 5, so plus or minus 5. 15 over 1 is 15, so plus or minus 15. So that exhausts that denominator. We move on to the next one, 2. 1 over 2 is a half, so plus or minus a half. 3 over 2 is 3 halves, so plus or minus 3 halves. 5 over 2 is 5 halves, so plus or minus 5 halves. 15 over 2 is 15 halves, so plus or minus 15 halves. All right, so that's that denominator. Now 1 over 3 is a third. 3 over 3 is 1, we already have that. 5 over 3 is 5 thirds. 15 over 3 is 5, we already have that one as well. Now let's do 6, 1 sixth. 3 over 6 is a half, we already have that. 5 over 6 is a new fraction. And then 15 over 6, so let's see, 15 over 6, those are both divisible by 3, so we get 5 over 2, and we already have that one as well. So these are all of our rational zeros that we could potentially have in this polynomial function. So next one, find the rational zeros of the polynomial. So we got our graphing calculator. Let's see which ones that we have. And then remember, we show our work and whittle this thing down a little bit using synthetic division. So if we have 2x to the third power minus 5x to the second power plus x plus 2, and graph it out. Looks like we have a 0 at, well, somewhere in between 0 and 1, and then maybe at 1 and 2. Let's check the table to verify that. Yeah, at 1 and 2, we have zeros. And then in between 0 and -1, we're going to have a 0. And I know that because of the intermediate value theorem. Since I go from the y value of 2 to the y value of -6, the only way that I could do that is if it passes through 0 somewhere in between there. So in between 0 and -1 for x. Okay, so if I already know that 1 and 2 are zeros, then I would just use synthetic division to kind of break it down a little bit, because I know that this is a third degree polynomial, so that means I'm going to have 3 zeros, and I already know 2 of them, 1 and 2. So let's find that third one. All right, so let's use synthetic division. Let's use the 1 in the corner, and then we use the coefficients 2x to the third minus 5x squared plus 1x, and then plus 2. All right, and then drop down the lead value, and then whatever the remainder is, it should be 0 since it's a 0. All right, so here we go. 1 times 2 is 2. 2 minus 5 is -3. 1 times -3 is -3. -3 minus 1, plus 1 is -2. -2 times 1 is -2, and sure enough, we get 0 there. Our next 0 is at 2, so then we just continue on, use synthetic division again with 2, and whatever remainder is, it should be 0. That's how we can tell if it's a factor or a 0 from there. 2 times 2 is 4. 4 minus 3 is 1. 1 times 2 is 2, and we get 0. So this gives us a linear factor. So that's going to be 2x plus 1. And that's how we can find our last 0. Just set it equal to 0 and solve. If I subtract 1 from both sides, I get 2x equals -1. Then divide by 2, and I get x is equal to -1/2. And -1/2 ends up being our last 0 that we needed there. And just to prove that -1/2 will work as well, if I do -1/2 on the synthetic division algorithm from the very beginning, 2, -5, 1, and 2, I'll get 0. Check it out. So if I do 2 there, 2 times -1/2 is -1. -1 and -5 makes -6. -1/2 times -6 is a +3. 3 plus 1 is 4. 4 times -1/2 is -2. And check it out. See, we get 0 either way. All right, so that's all 3 of our zeros. Let's find the real zeros now of this polynomial. So we're going to graph it out. So clear that out. X to the third power, x to the third, minus 19x, and then minus 30. Graph. And it looks like we've got zeros at -3, -2, and +5. So since this is a third degree polynomial, that's all of them. So let's double check it on our table just to make sure. -3 is a 0, -2 is a 0, and 5 is a 0. Sweet. So we know all the numbers that we're going to use with synthetic division. So let's go ahead and practice that. So we have 1x to the third power, 0x squared, so we put a placeholder there, -19x, and then -30 for the constant. We should get 0 for our remainder if we use one of the zeros. Let's start with -3. All right, so 1 times -3 is -3. That gives us -3. That's 9. And then that's 30. Yep, so that works. And then we'll use -2 for the next one. We should end up with a remainder of 0. Let's see. So -2, -5, +10. Yep. All right, and then the last part of it is once we get it down to a linear term, that's x minus 5. So set it equal to 0 and solve. So add 5 to both sides and you get your last 0, x equals 5. So that's all our work that we need to show, and those are our zeros right over there. It's pretty neat when the calculator gives you all the answers that you need, because then you know exactly what you need to do for showing the work. Okay, let's check out number 15. We should get 4 zeros from this, and this says mysteriously find all the zeros instead of find all the real zeros or rational zeros. This tells me I'm probably going to end up with an imaginary solution or two, so let's verify that that's the case. First graph it out. So y equals x to the fourth power plus x to the third power minus 8x squared minus 9x and then minus 9. So graph it out. Let's see if it gives us any zeros that we can work with. All right, so it looks like we have -3 and +3. Let's verify that. So go to the table. Yeah, -3 and +3 work. Cool. So we've got 2 of the zeros. That can at least, shrink this down to a quadratic potentially. So it should be pretty easy to manage it from there. So let's see here, 3 and -3. So we do. Let's start with -3. Why not? And then we have let's see, x to the fourth power. So that's 1 x to the fourth, 1x to the third, -8x squared, -9x, and -9 for the constant. Under our constant, we should end up with a 0. So let's use synthetic division here. 1 times -3 is -3. 1 minus 3 is -2. -2 times -3 is 6. 6 minus 8 is -2. -2 times -3, that's going to be +6. 6 minus 9 is -3. -3 times -3 is 9, so sure enough, that cancels out. Now let's use 3 for synthetic division. 1 times 3 is 3. 3 minus 2 is 1. 1 times 3 is 3. 3 minus 2 is 1 again. 1 times 3 is 3, and we get another remainder of 0. And this gives us a quadratic, x squared plus x plus 1. And this one we can't factor, so we're going to use the quadratic formula to find our last couple zeros. Because remember, we already have 2 of them, and we have a grand total of 4 that we need to find. So we already have -3 and 3. Now let's get those imaginary zeros from here, or irrational zeros, as the case may be. I'm pretty sure it's going to be imaginary, though. Let's verify that. So our a value is 1, our b value is 1, our c value is 1. So that's going to be pretty easy to plug in. Negative of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So we have -1 plus or minus the square root of, that's going to be 1 minus 4, so -3 over 2 times 1, which is 2. Just move the negative out front into an imaginary value, so we have -1 plus or minus I times the square root of 3 over 2. Can't reduce it any further, so that gives us our other 2 zeros. We have -1 plus I times the square root of 3 over 2, and then -1 minus I times the square root of 3 over 2. That's 1, 2, 3, 4 zeros, and we're all done with that one. Okay, next, it says to write this polynomial as a product of linear factors. Really, we want you to write it down as linear factors or irreducible quadratics, because they're, irreducible quadratics, they look a little bit nicer than the linear factors when you have imaginary solutions or irrational solutions. So I'm going to actually kind of go a little off script and do both of these, okay? Just linear factors and then also irreducible quadratics. And then you can tell, which ones look a little bit nicer. Okay, so first things first, as always, just graph it out. So let's graph it and see if we can get any free zeros off of it. So let's see here, x to the fourth power minus 3x to the third power minus 9x to the second power, minus 3x, and then minus 10. Graph it out. And we have negative 2. And it looks like 1, 2, 3, 4, 5. Okay, so negative 2 and positive 5 should work with synthetic division. Let's get a clean sheet of paper out here. I'm using a lot of scratch paper for this stuff. Okay, here we go. All right, so negative 2 is going to go in the corner there. And then I have 1x to the fourth, negative 3x to the third, negative 9x squared, negative 3x, and negative 10. So we should have a remainder of 0. Let's verify that. So 1 times negative 2, negative 5 times negative 2, 1 times negative 2, and then negative 2 times negative 5. Yep. All right, so another 0 that should work is 5. So plug 5 in. You should get a remainder of 0 at the end there. So 1 times 5, 0 times 5, 1 times 5, yep, 0. And we're left with this nice little quadratic here, x squared plus 1. You can use quadratic formula on it. Your a value would be equal to 1, your c value would be equal to 1. So it'd be pretty easy. And then your b value, there's nothing there, so it's 0. So that should be pretty easy. I'm just going to use the square root method to solve it, though. So if I set it equal to 0, if I subtract 1 from both sides, I get x squared is equal to negative 1. Then if I take the square root of both sides, I get x is equal to plus or minus the square root of negative 1. And the square root of negative 1 is really just I, so it's plus or minus I. So our two remaining zeros are going to be I and negative I. So now let's put together these linear factors. So the factors are just going to be like the first page of the review, where we have the zeros and we put together the polynomial. So same thing here. We do from negative 2 we get x plus 2. From 5 we get x minus 5. And then for the rest of the linear factors we get x minus x minus I, and then also x plus I. So those are all of our linear factors. Now, if you wanted to write it up as a product of linear factors and irreducible quadratics, it starts off similarly. It's going to be x plus 2. And then also x minus 5. And then your irreducible quadratic is that one that you stopped with over here. So it's x squared plus 1. I kind of like that a little bit better. You can still find this by foiling these two together if you wanted to. And in fact, I'd recommend doing it just for some extra practice. But either one of them they're the same anyways. I'd prefer this. I think in the test we probably ask you just for linear factors. But if you wrote it down with linear factors or irreducible quadratics, I'd be content with that. As long as you had your zeros and you showed your work. Okay, next up, number 17. So this says find a polynomial with real coefficients that has these zeros. Okay, so I always want to check the imaginary ones to make sure that the conjugate's in there. So yes, we have 3 plus I, but we don't have a 3 minus I. So that means that 3 minus I is another 0. And then 3 minus 2i, we also have to have 3 plus 2i as a 0. So we have 5 total zeros, which means that overall we're going to have a polynomial with a degree of 5. So let's start writing out the easy one, the 2. So that's going to be a factor that's x minus 2. And then we have these other two factors here. So there's a couple different ways that you can find these extra factors that you're going to multiply in. And I'll show you 2 different ways that you can do them, and you pick which one you like better. So I've got 3 plus I and 3 minus I. So that means that I've got the following factors: x minus 3 plus I, and then also x minus 3 minus I. So if I distribute the negatives into both of these, I get x minus 3 minus I, and then also x minus 3 plus I. And now I just distribute everything in. So x times x is x squared, x times negative 3 is negative 3x, x times I is xi, or ix. So that gives us the first round of distributing in. Now I'm going to use negative 3. Negative 3 times x is a negative 3x. Negative 3 times negative 3 is a positive 9. Negative 3 times I is negative 3i. Okay, now let's do our last round of distributing in with negative I. Negative I times x is a negative ix. Negative I times negative 3 is a positive 3i. Negative I times I is a negative I squared. And remember that I squared is the same as saying negative 1. So that's a negative, negative 1. Okay, so let's combine like terms. I have x squared, negative 3x and negative 3x, which makes negative 6x. And then I have an ix and a negative ix, which cancel out. A 3i and a negative 3i, which cancel out. And then I have 9 plus 1, which is plus 10. So that means that one of my factors here is going to be x squared minus 6x plus 10. All right, so there's one of them. So that's one method to get this factor, okay? I'm going to show you a different method to find the other factor, which is for 3 plus or minus 2i. And you can decide which one that you like better. I prefer the one that I'm going to show you right now, but you know, to each their own. So if I set x equal to this, I'm going to try and turn this into a 0. So what I do is first subtract 3 from both sides. So I get x minus 3 is equal to plus or minus 2i. Then to get rid of the plus or minus and the I need to square both sides. All right, so if I square this, then that's the same as saying x minus 3 times x minus 3. And if I square this side, then I get 2 squared, which is 4, and I squared, which is I squared. So if I FOIL this part in on the left-hand side, I get x times x, which is x squared, x times negative 3, which is negative 3x, another negative 3x from these two, so negative 6x, and then negative 3 times negative 3, which is a positive 9. I squared is negative 1, so this is really negative 4. And turn this into 0, I just add 4 to both sides, and I get my quadratic factor, x squared minus 6x plus 13. So that's the same way that you can find this factor, just using a different method. So what do I get? X squared minus 6x plus 13. And then, so that is my polynomial, all factored out in factored form. If I needed to write it out in expanded form, then I just FOIL all these things together or distribute all of them together. But I don't have to do that according to this stuff. Next, use synthetic division to show that 3i is a 0 of this. So this is pretty cool. I'm just going to do exactly what it's telling me to do. So 3i is a factor. Is a 0 if I get a remainder of 0. So I'm going to use 3i in the corner for this polynomial of 1x to the third. So 1x to the third plus 4x squared plus 9x, and then plus 36. So 36 at the end there. Okay. So here we go. 1 times 3i is 3i, so 3i. 4 plus 3i is 4 plus 3i. Now I need to take 4 plus 3i, and I need to multiply it by 3i. So if I distribute it in, 3i times 4 is 12i. 3i times 3i is going to be plus 9i squared. Remember that I squared is negative 1, so this is really 12i minus 9. So this becomes 12i minus 9. And 9 and negative 9 cancel out, so I just have 12i. 12i times 3i. So let's see, 3i times 12i. 3 times 12 is 36. I times I is I squared. And I squared is negative 1. Negative 1 times 36 is negative 36. And check it out, we get a 0. So that shows that 3i is indeed a 0 of this polynomial. And we also know that if 3i is a 0, that negative 3i is, because it's its complex conjugate. So you can redo the same process with negative 3i, and you should end up with a 0 for that as well. All right, so for each of the following, we need to do A, B, C, D, E, F, G, H. Oh, good Lord. Let's see here. Use the lead coefficient test to determine the end behavior. Okay, so for part A, for each of these, let's see. Lead coefficient. So the degree is odd, lead coefficient's positive, so that means it points down on the left, points up on the right. And for number 20, it has an even degree and then a positive lead coefficient, so up on the left, up on the right. All right, part B. Use Descartes' rule of signs to determine the nature of the real roots. So we're going to have positive real zeros and then also negative real zeros. So let's see here. Counting up the number of times that the signs change, so positive to positive, positive to negative, so there's 1, negative to negative. So that means that we have 1 positive real 0 that we potentially could have. Okay, and then if I change the signs on the odd powers, I get negative 6x to the third plus 5x squared plus 19x, and then minus 10. So let's count how many times that changes now. So negative to positive, positive to positive, positive to negative, so 2. So I could have 2 negative real zeros or 0 of them, because you go down by 2s just in case there's any imaginary solutions. So for part B here, Goes from positive to positive, positive to negative, that's 1, negative to negative, and then negative to positive. So 2 positive real zeros. Let's check the negative real zeros. So change the signs on the odd ones. So we have x to the 4th minus 4x to the 3rd minus 28x squared plus 32x plus 64. Then count the number of sign changes again. So positive to negative, negative to negative, negative to positive, and then positive to positive. So 2. So we have 2, 0 for both of them for the real zeros. All right, next part C, determine the possible rational zeros. Okay, so that's the whole list of the factors basically. So let's see what this gives us. So we have 10 in the top, 6 in the bottom. So 10 is going to be 1, 2, 5, and 10. 6 is 1, 2, 3, and 6. Oh boy. All right, so with the denominator of 1, we have plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. And then with the denominator of 2, we have 1/2. 2 over 2, which is 1, so we can skip that one. 5 over 2. And then 10 over 2, which is 5, so we can skip that one as well. All right, now let's use 3. So 1/3, 2/3, 5/3, and then 10/3. Now let's use 6. So 1/6, 2/6, which is 1/3, which we already have, 5/6, and then 10 over 6, which is 5/3, which we also have over here. So those are all of our possible real zeros. All right, part C over here, we have 64 and 1. So the factors of 64, oh boy. So we've got 1, 2, 4, 8, and then 16, 32, and 64. And then the denominator is 1, so that's going to be pretty easy. It's just plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16, plus or minus 32, and then plus or minus 64. So those are all of our possible rational zeros for that polynomial. Next, use synthetic division to find the rational zeros. Okay, so let's graph it out and see if we can, get any free rational zeros from that. So 6x to the 3rd power, and then we have plus 5x to the 2nd power, and then minus 19x, and then minus 10. Graph it out. So let's see what we have. We have a 0 at, it looks like -2, and then we have 2 rational ones. So that's not going to be very fun, but we can, kind of rationalize which ones they're going to be also. Oh boy, rationalize with rational zeros. I didn't intend that pun, but, there it is. So let's see here. -2 is going to be one of our zeros, so that goes in the corner, -2. And then for this polynomial, 6x to the 3rd, 5x squared, -19x, -10. All right, so let's see here. 6 times -2 is -12. 5 minus 12 is -7. And that's 14, and that's -5, and that's 10, so that one works out. Now we have this quadratic, 6x squared minus 7x minus 5. And what you want to do here, since you know that you're going to have some rational zeros, you might as well try to factor it because you're probably going to be able to factor it for those rational zeros. So let's try it out. 6 times -5. So we need to find numbers that multiply together to be -30 and add together to be -7. So that's pretty easy. It's -10 and +3. So then this will factor really nicely. So 6x minus 10, and then the other one is 6x plus 3. Divide out the lead coefficient, but the common factor. So that'd be 2 for this one and 3 for this one. So we get 3x minus 5. And then on this one, we get 2x plus 1. Okay, so if we set each of these factors equal to 0, we can solve our missing rational zeros. Equals 0. There we go. So add 5, divide by 3, you get x equals 5/3. And then subtract 1, divide by 2, and you get x equals -1/2. So these are the ones that are on our graph right here. So that'd be -1/2 over there for that 0. And then for this one, it's going to be 5/3 or 1 2/3 over here for that 0. Pretty neat, right? All right, so that's all the zeros, and that's using synthetic division to find them. Now write the function as a product of its factors. So that would be Let's see here. So for this 0, -2, we'd have x plus 2. And then we'd have these other two factors that we just found, which are 3x minus 5, and then also 2x plus 1. So it's completely factored now. Use the zeros and the y-intercept to sketch a graph. I mean, just make it look like you're graphing calculator and you're good to go. But, that's how we can do that one. So I'll leave G and H for you guys to kind of work on your own for graphing out. Okay, so now let's take a look at this one and find these zeros for this. We should have 4 of them. So y equals x to the 4th power plus 4x to the 3rd power minus 28x squared minus 32x, there we go, and then plus 64. Graph it out. Okay. Yikes, so it doesn't look like we're going to have any, some nice ones there, but we might have -2 and also at 4. So let's check the table. Yeah, -2 and 4. And we're probably going to have some irrational ones for the other ones, just to let you know, because we didn't have any fraction values for our potential rational zeros. Okay, so here we go. So we're going to use, what was it again? 4 and -2 for synthetic division. All right, so let's start off with using 4. All right, so we have 1x to the 4th, and then we have 4x to the 3rd, -28x squared, -32x, and 64. So we should end up with a 0 for our remainder. Let's see. So 4, 8, and then that's 32, and then that's 4, 16, and then -64. Yep. All right, and then for the other one was -2. So -2, 6, and then -8, and 16. Yep, that works out. So we end up with the following quadratic: x squared plus 6x minus 8. So once again, your standard way to find the zeros when it's an irreducible quadratic like this is to use quadratic formula. So let's use quadratic formula. So my a value is 1, my b value is 6, my c value is -8. So I have -6 plus or minus the square root of 6 squared minus 4 times 1 times -8, all over 2 times 1. Okay, so we have -6 plus or minus the square root of, let's see, that's 36 plus 32, so that's 68 over 2. Now 68, that's not divisible by 4, right? Oh, wait. Yeah, it is. It's divisible by 4. So 68 is the same as saying 4 times 17. Yeah, 17. So since I can take the square root of 4, I can reduce this further, because the square root of 4 times 17 is 2 radical 17, because the square root of 4 is 2. So that means that I can reduce this a little further. -6 plus or minus 2 square root of 17 over 2. -6 divides by 2, so I can get -3. And then the 2 divides out there, so it's -3 plus or minus the square root of 17. So those are my zeros. I've got so 4, not -4, but 4, -2, and then these 2 for my other 2 zeros. So to write it out as a product of its factors, if I want an irreducible quadratic, I'm just going to use this part of it right here. So I have, let's see here, from the 4 I have x minus 4. From the -2 I have x plus 2. And then I have my irreducible quadratic x squared plus 6x minus 8. So now it's in its factored form, and I'm good to go with that one. Okay, I think I'm done. Yeah, I'm done. So that is the end of the second page of the extra practice. And once again, even I'm kind of a little overwhelmed with all the amount of work that you have to do on this. But the good thing is, if you can do each and every one of these problems without any issue, you're guaranteed to get an A on the test. So just, stay patient. If you have questions, make sure to ask them. And that's it for the second page of the extra practice. Happy studying, and make sure to ask questions tomorrow.